there started a debate about storms and glutamate. So we decided, let's see if we can settle this debate or maybe fire it up further. So first of all, we'll the floor is yours.
Yeah, actually, this
question.
Actually, this is not the question I intend to answer first.
You intend to answer another one first?
Yeah, I thought we were going to answer the common Hall one first.
Oh, okay, right. I don't have a picture then.
Yeah.
Go ahead.
Okay, so the first question was what aspects of the churn number for the quantum Hall effect state have been confirmed by experiment, and how are they experimentally verified? And I think the churn number, I think, is more just a way of describing the phenomenon that is the quantum Hall effect. And this is from Bert Halperin, talking by Bert Halperin, how they experimentally measure the Hall conductivity is a standard Hall setup. And so you have your perpendicular magnetic field in the z direction, and then you apply a current in the x direction, and it creates a Hall voltage in the y direction. And then you can measure the Hall resistance, and therefore the Hall resistivity, and if you take the inverse, the Hall conductivity. And this indeed has experimentally been found to have these quantized plateaus, and meaning the conductivity is very precisely quantized to 1 in 10 to the 9th, in fact. And yes, I think he didn't say it, but I think it's quantized to 1 in 10 to the 9th. So, and in a sense, then the n equals 1, n equals 2, n equals 3, n equals 4 different Hall plateaus are the churn number. So the churn number is just a mathematical way of describing the different topological quantum Hall states, which are characterized by this certain churn number, which is related to like the number of level crossings of the Fermi level, the number of Landau levels that cross the Fermi level. And in a more technical fashion, it's also related to something called the Berry phase and the Berry curvature. But to answer the question, the churn number of the integer quantum Hall effect has been experimentally verified to a very high precision already. And as Bert Halperin says, it's independent of the precise shape sample choice of material, so it's very robust as a topological quantity should be. So that's what I have to say on that question.
Sorry.
I just wanted to say that if you actually calculate the quantum Hall, like the resistivity with Kubo formula, you get exactly E squared over H times the expression for the churn number.
Yeah.
So that's exactly.
Yeah. This is like the churn number seems to be basically the churn number is more like a mathematical formula of describing the physically topological quantized quantities. And so I think it's kind of weird to me to think about asking how do you measure or experimentally test the churn number. I think of it more as a descriptive paradigm, so to speak.
No, and I think what Mark said is correct. It is measurable because it gives you the number, which is the resistivity in units of the quantum.
Yeah, but what I mean is that the churn number is distinct from any physical thing. It's a mathematical idea that is applied to describe various things. In this case, the integer quantum Hall resistance is a churn number, but the churn number by itself is a mathematical idealization that's been applied to like the various particular phases. That's right, but I mean, I think that's just semantics. The point is, it's been verified experimentally.
More questions? I'll go to the next one. This is also still yours, right? Let's continue then, and then I'll continue.
Yes.
So with this one, 5.
Let's
go.
Okay. This is what is the effect of the magnetic field on a fractionalized Fermi liquid state? Yeah.
Wrong button, sorry.
Okay, so actually, I didn't really know the answer to this question very well because I didn't know much about this, and so that's why I asked Matthias about this. And as he said, it's not so simple. This is something I found before I heard his recent talk and before I asked him the question just now. But I think, as he said, if you apply a field large enough in a fractionalized Fermi liquid state, it'll automatically become trivially polarized state. But then, depending on the microscopics of the spin liquid that is coexisting with the conduction and particle hole pairs, you may or may not get interesting things in intermediate regimes. And so actually I think this was from a paper in 2003 at PRL from Santil, Sakta, and Voita, where they observed a metamagnetic transition. Well, actually they predicted that they would experiment with a metamagnetic transition if you got to a certain critical field. And so I think, I think as I said, as Matthias said, it is not such a clear, straightforward answer on what as in there's like no one answer on what is the effect of a magnetic field on the fractionalized Fermi liquid state. I think it very much depends on the microscopics in particular cases, but I think certainly this is something that is worth thinking about, and I think Matthias has already said quite a bit about it.
Maybe Matthias, do you have something to add? The idea is that lecturers should also, right, the comment on what
I
they
was
think
trying
about
to
that.
find you in the audience.
Well, I mean, this is really a complicated issue because, as I said, it depends on the nature of the spin liquid component. And this statement, which you quote there, is for a gapped spin liquid, which is fine. And then there's little magnetic response at low fields, and then once you close the gap, you get an onset of something, and this will be a second-order metamagnetic transition, as written there. If, in contrast, you would have a gapless spin liquid, which is also possible, then of course things would be potentially different. And again, the question which is independent of this discussion is then what really happens at higher fields? Do you destroy this topologically ordered phase? And how potentially does this phase, which is talked about there, then cross over or as a transition into a conventional polarized Fermi liquid? And all these are issues which can be worked out in some simple field theories, but those are not really satisfactory. So there's wide open field here.
Not satisfactory because you expect quantum fluctuations to be.
No, one thing, okay, I didn't detail this in my talk, but one thing which is not satisfactory, so I said we have a certain mean field plus fluctuations description, which is a working apparatus with which one can calculate things, but what is not really satisfactory about this description is what happens to the Fermi surface at the transition. As I said, one would expect for zero field now that the Fermi surface becomes critical upon approaching the transition from both sides, and then ideally one would have the coexistence of a small and a large Fermi surface at the transition point, both being critical. And this is not what the mean field theory is able to deliver, because it doesn't properly describe the phase which has no Kondo screening. So, I mean, that now goes into details of this mean field theory, but the Fermi surface evolution in this mean field theory is not the most appealing one can imagine. So, everybody is welcome to think about more clever mean field theories.
Matthias, and you say metamagnetic because the magnetization versus field exploring will be smaller than one? Why maybe that? For the second order transition.
No, this is not what this statement implies. It only implies that there will be an onset of magnetization and how this, again...
But the derivative is not diversion.
That probably also depends again on details of dimension and so on. So at the moment this is just the statement that in a metallic phase we get magnetization which is small up to some field, and then there is a kink at zero temperature, and then it stops.
But with a finite slope.
Yes.
So it's not really metamagnetic.
Well, metamagnetism, you know, in the experimental community is something which is used loosely for a rapid rise in magnetization without saying that it must be a jump.
All right. Like what we had in the previous Wiki session, I have the privilege of trying to answer my own question. So there was intended to be directed towards Zicheng Zhang, but I think he already left. So I was wondering when the quantum spin Hall state was first predicted theoretically, it was predicted by both Kane and Melee in 2005, and at the same time also by Zicheng. in 2006. I think they submitted the papers around the same times. So in the top paper by Kane-O'Malley, they predict this quantum spin Hall effect in graphene. So I was wondering now, is that still a possibility? Because at some point they moved away from graphene because the spin orbit coupling is not very big in graphene, and you need preferably a large spin orbit coupling, like in these mercury telluride quantum wells, and even for the 3D topological insulators, you also have pretty large spin orbit coupling, so you can do at moderate temperatures your experiments. In their original paper, they predict that they should be visible, I think, below 1 or below 5 Kelvin, something like that. But it turns out they were a little bit off. In principle, let me first say that for the model of Kane-O'Malley to work for graphene, you need the intrinsic spin orbit coupling, which will induce gaps of opposite signs at the K and K prime point, which will be then connected by this quantum spin Hall state. If you have any other type of spin orbit coupling, like for example the Rashba spin orbit coupling, that will be destroyed. So that will lift this inverted gap again. So you need your spin orbit coupling to be larger than your Rashba spin orbit coupling. In general, in most of the graphene experiments, graphene is on a substrate and you use a gate to tune your carrier density. So in general, the intrinsic spin orbit coupling will be smaller than your Rashba spin orbit coupling, so there's no chance of actually seeing this. But say you can remove your Rashba spin orbit coupling, you could see it. So that's what these authors argue after calculations. In undoped samples, you may have the reversed order where the spin orbit coupling is in fact, the intrinsic spin orbit coupling is in fact dominant. But then still we're talking about temperatures of 10 millikelvin. Okay, so you could say, well, we'll do it in freestanding graphene, then we don't have troubles with our substrate. But then there's another problem. A freestanding graphene is not very stable, so it starts buckling and rippling a little bit. This will create an extra spin orbit term, which also works against the spin orbit coupling we're trying to achieve. So, and to add to this, this picture may seem familiar because it popped up earlier today already in Jörg's lecture, regarding the spin orbit coupling in graphene, where it's pretty relatively large at the gamma point, but at the relevant point for our experiment, it's rather small, which corresponds to this 10 millikelvin. This is, by the way, all three authors find roughly the same number. So then I got thinking, okay, is this then possible? Because, okay, let's say we have a freestanding graphene, and let's say we don't have Rashba spin orbit coupling. Can we reach 10 millikelvin? Yeah, of course we can reach nanokelvins or microkelvins in cold atoms, but I found after a little bit of googling a paper where they measure the fractionalized quantum Hall measurement effect below 10 millikelvin. So in principle, this temperature is attainable in an experiment. But I think if you then go back to, okay, what could they do in the mercury telluride system and compare that to what you can do in graphene in this system that I've arbitrarily created right now. So we have freestanding graphene and we have to cool it down to very low temperatures. In the mercury telluride, they can play with the thickness of the quantum well, whereby they were tuning this band inversion. Well, you may have the ability to tune this band inversion by playing again with this Rashba spin orbit coupling, or maybe even with the rippling effect in your graphene, if you can really manipulate it like that. But as soon as you start tuning your density, what they're doing in the mercury telluride as a really telltale sign, you tune it into the band gap, and then you see this quantized conductance only in the quantum spin Hall state. As soon as you start doing that in graphene, I think you're screwed through the Rashba spin orbit coupling. So I got looking a little bit further into this rippling kind of effect. I was looking for whether they were already able to stabilize freestanding graphene without rippling, but I think it is a sort of an intrinsic effect of freestanding graphene, which this is, by the way, bilayer graphene, this is another article I saw on Physics World a while ago, and I remembered it suddenly. So they associate this as bilayer graphene and this is a curtain. They introduce a new sort of quasi-particle which seems to scale to various length scales. So I would like to stop the discussion of the graphene here and saying that I think that will win the Ig Nobel Prize this year. Any questions regarding this point? Oh, thank you. Then we'll go on to you.
Can I ask a question?
Yeah, sure.
So what happens if we're talking about graphene here with carbon. In principle, people have control over AFM, moving atoms around. What prevents them from taking some really heavy atom with really big spin orbit and making an artificial hexagonal lattice out of it?
In principle, nothing. I think, I haven't looked into this, but I think even in the cold atom community, people may already be working on creating these kind of artificial lattices where you can see something like the quantum spin Hall effect or topological insulator effects in those kind of systems, yeah.
I can take something which would have intrinsic spin orbit bigger than the radical from the substrate, which is what you require. The question is how big of an array should they have, because quantum Hall to some extent they need to have an edge separate from the bulk, right?
Yes. Well, if you look at, for example, the topological insulator effects, where you have these layered structures. So take, for example, bismuth selenide. They have these quintuple layers, which are about a nanometer thick. So the 5 layers is a nanometer thick. And I think, as Yucheng also showed in his talk, you need at least 3-5 quintuple layers before you actually decouple both sides. So before the surface states or the edge states in the quantum spin Hall effect don't talk anymore to each other. And that also depends on your Fermi level. So the higher you are in the Dirac cone, the further these states will extend. So I guess you need at least a structure of 5 nanometers, which would take some students a lot of work with the AFM, I guess.
Hey, I'm the theorist. I can give you a tremendous lot of work. That's what I do.
So yeah, that would be my answer. I don't know which one you need.
Right, also this
No?
so that one is the Wiki
This is the last one? Oh, no. At least, no, I don't think I have. Okay. Maybe, questions?
Yeah, probably. Okay, so the first question was basically already answered. It was what was the meaning of fractionalized in these fractional spin liquids. Just as an illustration, we got this slide out of the talk just to look at it again and explain it with this. So the basic idea is you look at the elementary excitations, and when you start, you've got electrons as your elementary particles making up your system. So these have got a charge of -e and a spin of 1/2. So if I now construct any usual excitations out of this, I can either construct fermionic excitations with a spin 1/2 or spin excitations of a combination, for example, of a particle and a hole. Those don't have a charge then, but they have integer spin. So in this spin liquid, now you can have these spin-on excitations, which have a spin 1/2, but don't have a charge. So that's why you have a fractionalized electron, because you separated the spin 1/2 degree of freedom from the charge degree of freedom. So did this now get completely clear with this picture, or any more questions? Okay. So the second question, I don't have a slide for. That was for this D-wave superconductor. There the question popped up why on the BEC side, is this guy gapped? Shouldn't it be gapless or what? So basically it's about the BEC-BCS transition, the discussion, right? So on one side we have this BCS picture where the correlation length of my particles is a lot bigger than the mean distance of the particles. On the other hand, I am in so that's BCS. Probably all know these pictures. Here on the BEC side, you're in the limit where you've got strongly bound molecules, pairs of my original particles. And between these two guys, you have some sort of transition crossover. So for an S-wave superconductor, most of us know that that's just a crossover. And now the argument which probably got us to this question was for S-wave. You have a gap on both sides. Now it's important what does the gap mean here. So in our opinion, this just refers to fermionic excitations, which mean I want to break one of these pairs on this side or on this side. So on this side, I've got a uniform S-wave gap, which I have to overcome. In that sense, I'm gapped here on the BCS side. Here on the BEC side, I have bound molecules. If I want to break these, I again have to overcome this finite energy gap. So in this sense, I'm gapped on both sides, and I can continuously deform the thing here into the thing here. So that's why I can have a crossover. So now for D-wave, these BCS pairs have a gap function which has nodes, right? I mean, you have D-wave symmetry, so something like this. So you have here node lines where the gap goes to 0. So here I can have gapless excitations where I separate these particles, at least at these specific momentum points. While on this side I still have bound molecules, so here I have a gap to separate those sides. So in that sense, I can't continuously deform this state into that state, and that, I guess, was the argument in the lecture, that therefore I need to have a phase transition in between. Any comments? Yes?
I think, and there are people certainly here who know BEC better than I do, but I think one of the issues of the BCS versus BEC is that on the BEC side, the low energy excitation is not just breaking the pair, because on the BCS side, the phase stiffness is such that it costs you less energy generally to break the pair than to create something like a vortex.
Yes.
On the BEC side, I think it costs you actually less energy to create a roton, so to speak, right, than to break a pair.
Yeah.
So it might be that the gap that we're talking about on the BEC side is actually the roton gap, and not just the binding energy, which went way up. But again,
Yeah.
but I think that's why it's gapped, because certainly the pair sort of became tightly bound, but that energy is extremely high. So the gap is much lower, I think.
So that's why I said probably you're talking about separating those pairs and fermionic excitations. But any other thoughts?
Well, I have a comment, and I think it's independent of Ilya's comment / question. I think the argument that you've given is I'm not going to say whether it's correct or not, because I'm not sure, but it certainly has been given before.
Yeah.
And so, 2 points for coming up with that one. Now here's a generic way of understanding the question on the BEC side. We still have something which is d-wave in nature. That means there's got to be a pair wave function, which is, or let's call it an order parameter for want of a better word, which does still have zeros because it's d-wave. But that's not the same thing as the energy gap in the system. And so that the chemical potential is, of course, doing very weird things from our usual perspective on the BEC side. So I think that's the origin of the effect. But then that leads me to the following question. Supposing I start from the opposite limit and I play around on the BCS side a little bit. So supposing I make a highly anisotropic S wave in the BCS limit with nodes, and I can do that. And then I go to the BEC limit and I use your argument and I have a gap again. So I should have a transition in that case simply because I had nodes in the S wave case. That's again a question. Tzu-Cheng is gone.
Yeah.
But that's the way it seems to me. Any other comments?
I also have a question, because if I understood correctly, it's that you need a P-wave superconductor that has a non-trivial topology, and only then you get phase transition. So if I understand correctly, a D-wave can have a crossover to a BC.
That's not what Zhang said. That's why this question was posted.
I think he also said there was a phase transition between these two. Not necessarily maybe that's a topological phase transition, but there was a phase transition.
So this phase transition has nothing to do with
Right,
topology.
right.
But isn't the topology of the BC trivial?
Yeah,
Yes.
yeah.
So how?
Has nothing to do with topology. You said it right.
So is the topology of the conventional BCS D-wave, right?
Yes.
They're both trivial. So
Both trivial.
The question is whether I have a transition.
Yeah.
The topology is trivial on both sides. The question is whether there is a transition.
In one case, the transition is about the disappearance of the nodes in the D-wave case, or in the simple P-wave case. But in the P plus IP case, there it's about going from a topologically non-trivial to a topologically trivial state. So these are, in some sense, different things.
So,
Go ahead.
I already asked you the question, but maybe it's good to be clear. So if you object, it's
No, please go ahead.
okay. So when we talk about the this topological, not topological things, right? We need smooth information, right? But I mean, Shochet showed only the quadratic methods, right? Where the fermionic spectrums first, right? But here we talk about real systems with spins, right? So I mean, in principle, both, if you take S wave, right, BC to BCS, right, both systems are couplets, right? So because here we have the zero sum modes in the BCS side, right, which is couplets, right, and in the BC side we have folds, right? And then, but in order to make a smooth transition, you need the spectrum of the entire system to be coupled, right? So fermionic is not the only branch which we take care of, right?
You're looking at me.
No.
Oh. But I think Ilya was making somewhat the same point, right? You're saying that there are other...
Yeah, I think what Leonid is actually saying, that if I look at both gas
I'm
non-interacting,
Yeah,
there will be no gas,
No,
even once it condenses.
I'm going to the point of adiabatic theory, no? You have to have a gap for it to be adiabatically connected, right? But the gap is strictly speaking, if you take real system spin, right, there is no gap in any case. Because there's always a state in the system, not necessarily the fermionic nature, right? Which is supposed to constrict, right?
But that is,
So
I can start with the purely fermionic point. I think that from the point of view of the model, that is perfectly allowed. Except put in pairing and ask what happens after that in the two limits. I mean, and that's the question that you're answering, because I've been formulated. So you're right that in that sense, pairing means interaction, so strictly speaking, it's not a non-interacting system. But on the other hand, that's the only interaction we're considering. And let's agree that we'll decouple it at the mean field level.
But
Also, if pairs are charged, then your Goldstone node is gapped. Yes.
Look, that's the reason why he's showing the quadratic Hamiltonians, right? But he's asking about the generic things. So what I'm saying is that if you just write Hamiltonians backends, then anything is possible, right? But if you take into account the real things, then
Well, I don't know what, the real things are loosely defined for me at this point. Which real things are we talking about?
it's still
I certainly am allowed to write a Hamiltonian with pairs and treat them at the field level, in which case it's quadratic.
Oh yeah.
Let's not go beyond this because we're trying to answer the simple questions before we go to the complicated ones. Right? I mean, and that's the question that we're discussing, I think. But even in that case, depending on if the pairs are charged, for example, you will get the Goldstone that moves to plasma frequency.
Oh yeah, of course, sure. Yes.
We have other questions, I think, right?
Yes.
Yes, firstly, an apology for the quality of the figures. They were a little bit rushed and copy and pasted in LA notes.
It was better the other way.
Okay, so I was approached to do this wiki session because they only had certain theorists involved and they thought, it'd be some experimental questions, so see if they can get an experimentalist involved. So I'm sure the other experimentalists will realise I panicked a little bit when I saw the big page full of topological insulated and graphene. But there was an interesting discussion which broke out earlier on about strontium ruthenate and about at what point it can be called definitively a Fermi liquid, and then above that temperature whether we can class it as a good or a bad metal. And there's sort of a debate between sort of different bits of data that are in the literature. And so we thought, well, we might as well just go and get, find this data, and then I'll. So what I want to do is give you, kind of show you the data I found. It's not a system that I actually know. So I just sort of introduce the data and how I see it, and then hopefully bring in a discussion so we can work out if strontium ruthenate is a good or a bad metal above 20 to 30 Kelvin. So what we see here is we see some zero field resistivity data from Nigel Hussey's group, which I think was at Cambridge at the time. The line we see here is the C-axis resistivity. The other line following a nice t-squared curve is the in-plane axis. And in the inset we see that both resistivities plotted against t-squared below 20 Kelvin. So I'm just giving you a little bit more detail because I'm not sure you can all read the diagram too well. Okay, so the inset shows that below 20 Kelvin we've got both the in-plane and the c-axis resistivities are linear against t-squared, which is thought to show good Fermi liquid behaviour in all three dimensions. This is supported by NMR data, which I've also got here, but I didn't have time to look through. I'm not overly familiar with NMR. So I believe the lower of these two panels indicates, they've indicated TFL there, where they believe that we enter a Fermi liquid state below 25 Kelvin. So below 25 Kelvin, there seems to be good agreement that we've got Fermi liquid in strontium ruthenate. But then as we go above, we can see in the c-axis resistivity, it goes way off away from t-squared dependence. So in the NMR data suggests that we get to 25 Kelvin and we don't have a Fermi liquid anymore. The resistivity data suggests that we definitely have a Fermi liquid in all three dimensions before below 25 Kelvin, but above that we retain what is actually very nice t-squared dependence all the way up to room temperature in the planes, but not in the c-axis. And this is the two tied together whereby the magnetoresistance suggests that we get effects in the spins, which is what the NMR's picked up as well, that disturbs the c-axis conduction. And there'll be people here who can tell you a lot more than I can. And so, the c-axis is definitely non-metallic behaviour above around 30 Kelvin. But the question is really, which came out earlier on, is whether we can class strontium ruthenate as a good or a bad metal at high temperatures, considering that the planar conductivity is seems very good from resistivity, seems very tightly matching to these square companions, whereas the C-axis isn't. So I'd like to open the room to debate as to whether this makes it a good or a bad metal, and whether we can still class this as Fermi liquid behaviour, even though the C-axis resistivity suggests it is.
Well, it's just a question. I wanted to define the question. What do we call a good method and what do we call a bad method? Because certainly the point of deviation from t-squared behavior to me seems not a very functional definition. Because if I do make the same plot for copper, it will basically deviate at, roughly speaking, the same temperature, maybe even lower.
Much lower.
Probably 2 Kelvin, if I 5, something like this. So do we call copper a worse metal than strontium glutamate? I mean, so I'm a little bit, that metal is a little emotional. Irrational definition.
Be careful about the fact that
That depends on what temperature you're at and it's very.
so you are getting
What
completely different phenomena which
much
enter
more
in our values.
Yeah,
So it's only in the low temperature unit where other scattering processes are not there that you can see.
yes.
Yeah, certainly it seems from what I read briefly, it's around this point where we see it go off that you start getting, where the impurity scattering isn't the limit on the free path, and that's where you sort of okay, so Mark, I think you were involved with the discussion there.
Just a little comment. I mean, I don't want to argue whether it's a good metal or a bad metal, but so there's this, for people who are not familiar with the strontium gluthanates, there's this whole series of compounds in the Bunsen Popper series that start with this also the 214 compound that has one single layer, and then you go on. 327 has 2 layers, and 113, so strontium gluconate 03 is the full 3-dimensional structure. And if you look in this series, then you get to worse. At least if you look at these series and you look at resistivity data, then you get for the 113 you have linear behavior, so that's usually called a bad metal. And then for the 327, you also you enter linear resistivity behavior much earlier. Or you have something like Fermi liquid at very low temperatures, but then you enter in a T-linear regime. And so that.
Let me just first answer the question which was initially raised. So we put on our plot, we put strontium glutamate, I mean the 113 and 214. The question was which one of the two is more correlated. So one way to look at it is to compare the specific heat, the linear coefficient in specific heat, compared to what LDA gives you. And in 214, you get 38 millijoule per mole Kelvin square, and this amounts to an enhancement of 4 over LDA value, whereas in 113 you get 3.7. So that's why 113 was positioned a bit higher on the plot. And then another comment regarding copper. If you calculate the density of states, I mean if you do LDA calculation on copper, sure. I guess you get pretty good specific heat coefficient. Okay. Whereas here you get an enhancement which is 4. But I agree that looking at the resistivity is not the way to define.
I agree completely. I mean, if you can make a functional definition out of how much you have to renormalize the LDA mass to get agreement with whatever your favorite experiment is.
Yes, and another point, if you want to look at the temperature dependence, is the 1 over T1T measured by NMR, and in a good metal, in a Fermi liquid, you have Coringa behavior, meaning 1 over T1T will saturate, and it certainly does not. I mean, they didn't show here. Oh, there is one. Yes, so you see a saturation in the lower plot, which does not happen until 25 minutes. So that's why
there's only saturation here.
I think it's a measure of correlations. That's absolutely correct. Right. I would argue that the bad metal, good metal, one can look at residual resistivity. That, to me, what means good metal or bad metal. You know?
Well, no, I mean,
Correlated metal is a different story.
Sure, sure. But okay, the main discussion started from it's fermi-liquid or not. And
yeah, but also, I mean, if in C-axis you see insulating behavior and in AB-axis metallic, this, I don't know.
That's how you have a rapid
No, no.
But that's actually still not completely resolved why that happens. There's different proposals. Structure movement 214 and so on.
Well, we have promising GADI plus DMFT results on this.
right, final comment. So I have no, not anymore.
I think it's irrelevant. Go ahead.
Sure, sure.
Okay, so they are so excellent. Then I generate by the question by myself. So question is, what type of non-fermi liquid exists in quantum critical region, especially for the heavy fermion compounds. Non-fermi liquid sounds very exotic. So at first I hear this one, it including Bosonic liquid or something. But actually this one indicate more specific things. And this one is a typical phase diagram of the heavy fermion. Some parameter delta, and right hand side is fermi liquid, and here sometimes there is superconductivity, and here is some magnetic product. And then, as shown in lecture, this compound shows good non-fermi liquid behavior. That is, specific heat is the universal critical behavior looks like that, and then this one is crushed in non-fermi liquid. So I was wondering why it is good non-fermi liquid. So then I look for some difference, and actually there was a good difference, and yeah, that is this one. There is some theory about this quantum critical point that is called self-consistent renormalization by Moria, and then they predict this predict some critical behavior for four types of things. Okay, so here this one is shown. This one is anti-ferromagnetic, but suppose this one is ferromagnetic, and 2-dimensional, 3-dimensional, they get some good analytical representation. And here, for anti-ferromagnetic, this one is different. And then, if I refer the previous result, this one is anti-ferromagnetic, so probably this one is 2-dimensional things. I don't know, but actually this one. Then, then I'm wondering why it can be done by analytically, and because usually to detect the universality class is very difficult, but here they get some analytical expression. But now I'm thinking that this region is connecting to the trivial high temperature limit directly without any phase transition. So basically, if I am correct, this one can be derived within the one-body program. So probably we can get this kind of analytical representation. That's it. So do you have any comments?
Well, if there are no comments, then we'll wrap up this wiki session. There were, we think we answered most of the unanswered questions still left on the wiki page. There were a couple of questions which have already been asked by the respective speakers to whom the questions were addressed. So if you haven't seen your question here on the previous wiki session, I would suggest go back to the page, maybe your answer is there. I believe there was one question relating what happens to a topological insulator when you apply a magnetic field. It was along those lines, right, that question? Which really large magnetic fields, I believe that got already answered in the lecture. They show some experiments with where you do see the lambda levels appearing, and at some point you'll definitely break the time reversal symmetry, destroying your topological insulator state. In fact, in the quantum spin Hall effect, they see that they can destroy this H state rather quickly with a magnetic field. So with that, thank you very much.